Gauss's method and Gibbs' method were focused on finding a unique orbit definition based on 3 different measurements of the orbital radius vector at 3 different times. In these cases, we were able to get away with not knowing any of the orbital velocities by having multiple measurements, and the minimum number of such measurements of just the orbital radius vector is 3, with 3 associated times. There's an analogous problem where you only have 2 measurements of the orbital radius vector, along with the single time between those measurements. And this is not enough to constrain a unique orbit connecting the 2 points represented by those 2 orbital radius vectors, but it is sufficient to calculate all of the possible orbits between those 2 points. This case, known as Lambert's problem, is a boundary value problem and is more applicable to trajectory planning rather than orbit estimation from measurements, because it exactly describes the case where you wish to send a spacecraft from one point in space to another point in space, following the path of a 2-body orbit about some central body. So here's a description of the problem. We have a point P1 that is in orbit around some central body at focus F, and we have the radius R1, which is our P1 rel F, at a time T1, that is our time of departure. We wish to end up at a point P2, say another body orbiting the same central focus F at some time T2 later. This will be our time of arrival. And we have the ability to calculate the radius R P2 rel F, which we will call R2. Since we know R1 and we know R2, we can calculate the 3-dimensional angle between them, which we will call delta nu. And our problem statement is to find all possible 2-body orbits with F as the central body that patch between P1 and P2. If we assume a Keplerian orbit that connects P1 and P2 with the central body at F, then there must exist a vacant focus at some location in space, F star, what we've previously called F prime. If the transfer between P1 and P2 is, for example, an ellipse, we also know that the segments connecting F to any point on that ellipse and F star to any point on that ellipse, the things that we previously called R and R prime, have to equal twice the semi-major axis of the transfer. And so we can write these 2 relationships, the segment P1F and plus the segment P1F star, and the segment P2F plus the segment P2F star, both have to equal 2A. And we can rewrite each of these as the segment between point P1 and F star and the segment between point P2 and F star must each equal 2A minus the radius magnitude R1 and R2, respectively. If you stare at these equations, you'll see that they represent a segment equaling a constant value, and that is a description of a circle. So both of these equations represent circles centered at P1 and P2 respectively, and F star has to lie at the intersection of these 2 circles. So by making these assumptions about the problem, that there exists a 2-body orbit that connects P1 and P2, we have instantly provided ourselves with a method of discovering where the vacant focus of that orbit lies. Graphically, this looks as follows. Here is our original setup. Here is the circle centered on P2, whose radius is 2A minus the norm of R2. And here's the circle centered at P1, whose radius is 2A minus the norm of R1. And again, A here is the semi-major axis of your transfer. And these 2 circles can have up to 2 intersections, and the F star for a given value of semi-major axis A of the transfer trajectory has to lie at the intersection of these 2 circles. Selecting the transfer orbit automatically determines not only the locations of the vacant focus, it also sets the specific energy, because you will recall that for all orbits, the specific energy is equal to the gravitational parameter over 2A. In this case, this is the gravitational parameter of the central body, whatever the central body is at F. If it's helpful to you to have a mental model of this, just think interplanetary transfers. F is the sun, P1 is our departure point from near Earth space, and P2 is the arrival point at somewhere else. So for example, say we are going from Earth to Mars. We start at the location of the Earth at whatever our launch date is, and we arrive at Mars approximately 9 months later, because that is how long most optimal transfers to Mars take. And we follow some portion of an ellipse between Earth and Mars through an angle delta nu about the sun. Having selected the semi-major axis of our ellipse sets the specific energy of that transfer. If we select a positive semi-major axis, then we will have an elliptical transfer. If we set a negative semi-major axis, then we will have a hyperbolic transfer. Down selecting to one of these possible vacant foci locations will set the eccentricity of your transfer orbit, because the segment f star is equal to twice the linear eccentricity, so 2AE. So for example, in this case, we have chosen this to be the actual vacant focus that we will use for our transfer orbit, which automatically generates this transfer orbit. You see that it maps between P1 and P2. And so by the selection, we've already chosen the semi-major axis, and now we have the eccentricity. If we had selected this other vacant focus, which we will call F2 star here, then we would have gotten this red transfer ellipse, which would have the same semi-major axis as this blue transfer ellipse, whose vacant focus is F1 star, but with a different eccentricity. We have now provided ourselves with 4 possible paths between P1 and P2. We can take the blue ellipse, either the long way round or the short way round, or we can take the red ellipse, either the long way round or the short way around. So for elliptical transfers, for feasible positive semi-major axes of the transfer ellipse, we automatically generate 4 possible solutions. There also will always exist a unique elliptical orbit that minimizes the specific energy of the transfer. Remember, we have these 2 governing relationships. These are the expressions that gave us the original geometry of the 2 intersecting circles that allow us to establish the location of the vacant focus. If we add all of these together, and recalling that this is the norm of our vector R1 and this is the norm of our vector R2, we will get, so the magnitude of R1 plus the magnitude of R2 plus the 2 segments between P1 and P2 and the vacant focus F star altogether have to equal 4 times the semi-major axis of the transfer ellipse. The specific energy is negative mu over 2A. If we wish to minimize the specific energy, then we need to minimize A. The smaller the A, the larger the magnitude of this fraction, and therefore the smaller the negative value of the specific energy. Since R1 and R2 are constant, we can't change them, that's part of the problem statement. What we're really talking about is minimizing this. You minimize P1 F star plus P2 F star by placing F star on the chord between P1 and P2. And so the minimum location of the vacant focus will be on the line connecting P1 and P2. And in this case, there is only one possible location of the vacant focus because these 2 circles will only touch at this one location. They will not have 2 separate intersection points. And therefore, we can calculate the semi-major axis of the transfer associated with the minimum possible specific energy of the transfer as a value S over 2, where S is the sum of the perimeter of this triangle divided by 2. So that's the vector R1, R2, plus the relative vector R1, rel2, all divided by 2. Using what we know about two-body orbits, we can then figure out the eccentricity of this minimum transfer, which will be given by the square root of the quantity 1 minus twice the semi-parameter over S, and the semi-parameter will be equal to the norms of R1 and R2 multiplied together, scaled by the norm of the relative position vector times the quantity 1 minus cosine of the transfer angle delta nu. So far, we've established that if we select a positive semi-major axis representing an elliptical transfer, we can get up to 2 full transfer ellipses and 4 transfer paths by following the 2 ellipses in 2 different directions each. But what about all of the other possible transfers? Can we characterize all of the possible orbits between P1 and P2? Let's go back to these relationships. And now let's subtract these to find That is, the line segment P1F star minus the line segment P2F star equals the norm of our vector R2 minus the norm of our vector R1, again, a constant based on the problem statement. One segment minus another segment equaling a constant is a geometric representation of a hyperbola whose foci lie at P1 and P2. Now let's be very clear about this. This hyperbola is not a transfer orbit. Rather, this describes the locus of all possible locations of the vacant focus F star. The semi-major axis of this hyperbola is given by the difference between R1 and R2 divided by 2. Recall that by our convention, the semi-major axis of a hyperbola has to be negative, and so to ensure that, we take the negative of the absolute value of half of this difference. And similarly, the eccentricity, which for a hyperbola has to be greater than 1, is given by the magnitude of R1 rel 2, this segment between P1 and P2, scaled by the difference between R1 and R2. And again, we take the absolute value just to ensure that we always get a positive value greater than 1 for all cases, whether the norm of R1 is greater than the norm of R2 or the norm of R2 is greater than R1. Remember, these parameters do not describe a transfer orbit between P1 and P2. Rather, they describe the locus of possible locations for the vacant focus of that transfer. The filled focus of that transfer is always the central body of this problem. The hyperbola is placed such that the left branch passes through the filled focus. Remember, if the filled focus and the vacant focus coincide, that is a description of a circular orbit. And so we have to have the possibility of the filled focus coinciding with the vacant focus. And then that places the right branch of the hyperbola such that it passes directly through this minimum energy point, the FM star that we've previously found as the vacant focus of the minimum energy elliptical transfer. Because the location of the vacant focus uniquely determines the transfer orbit between our 2 points in time and space, we can use this to create an incredibly powerful visualization of all possible transfers in the Lambert problem. And this visualization is largely based on one published in Kaplan's 1976 book. The setup is the same as before. We have a central body at focus F. We have a point P1 at time T1, that is our departure point, and we have a point P2 at time T2, that is our destination point. We have already shown that we have 4 families of ellipses, and now, following Kaplan, we are going to label them E1, E2, E3, and E4. E1 and E3 are pairs of short and long ways for one set of ellipses, and E4 and E2 are the pairs of short and long way for the other set of ellipses. And they are shown diagrammatically here. So here's E1, short way, E3, long way, and E4, short way, E2, long way. In addition to the infinite number of elliptical transfers, we have 2 unique parabolic transfers, one passing below the filled focus and one passing on the opposite side. The velocity of the orbits for these transfers will be the escape velocity of the central body. This upper parabola bounds the E1 departure region, and on the other side, the E3 departure region. And each of these is bounded on the other side by the single unique ellipse corresponding to the minimum energy focus. So on this blue bounding curve, the velocity is the velocity associated with the minimum energy ellipse. The other elliptical transfers, E4 and E2, are bounded by the other parabolic transfer, E4 on the bottom and E2 here on the top, and also by the minimum energy curve here. The vacant foci corresponding to all elliptical transfers lie on this right-hand branch of this hyperbola. The 2 families, E1, E3, and E2, E4, branch off at that minimum energy focus. So any vacant foci locations lying on this part of the right hyperbolic branch belong to the E2, E4 family, and any vacant foci on this part of the hyperbolic branch belong to the E1, E3 family. The left-hand branch of the vacant focus hyperbola describes all possible hyperbolic transfers between P1 and P2. And we have 2 possible families. We have the H1 family that are transfers going above the R1 rel 2 line, and we have the H2 family that are transfers going below the filled focus. The H2 vacant focus location branch starts immediately below the location of the filled focus and then goes onwards to infinity down the branch of this hyperbola. However, the H1 branch starts at this F0 star vacant focus location. The significance of the F0 star vacant focus is that this describes the orbit in which P1 and P2 are connected by a straight line. And that's not physical. In order to get a straight line orbit between P1 and P2, that essentially means that you would be ignoring the gravitational effects of the central body at F, meaning that you would need infinite velocity. So this is, again, a strict bounding point. All of the H1 hyperbola have their vacant focus above this F0 star location. This also means that there are no departures possible within this region. Any hyperbolic transfer that departed within this region of space would fly in front of the filled focus, again, meaning that it was ignoring the gravitational effects of the central body. This locus of physically impossible departures corresponds to this dashed region of the left-hand branch of the vacant focus hyperbola. And again, here we have diagrammatically shown the H1 and H2 transfers. We can provide an alternate visualization of all of this by filling in the full space of departures. So this is exactly the same diagram as before, except now we have shaded the full regions of the orbits. Above the R1 rel2 line and below one of the parabolic transfers, we have the H1 region. So all hyperbolic transfers of type H1 lie within this shaded region. Similarly, all hyperbolic transfers that go below the filled focus and above the second parabolic transfer give us this H2 region. The E4 and E2 regions are shown here. So here we have all elliptical transfers that have their short way below the filled focus. And finally, we have E3 and E1. And so all ellipses that have their short way above R1 rel2 lie in this region of space. The main takeaway here should be that the location of the vacant focus really controls everything. And so simply by choosing any spot anywhere on these branches, here or here or here or here, you can calculate the resulting transfer orbit. Let's take a quick look at how that works. Here we have the same diagram generated in MATLAB. The data describing these two branches of the vacant focus hyperbola are stored in two variables called rhype and lhype. So let's start by picking a point close to the bottom of the right hyperbola towards the start of the array. That should put us in the E1, E3 family of elliptical transfers. We'll choose the 100th element of the array, which as predicted puts us somewhere down here. And we will use a piece of utility code called vac focus to transfer, vacant focus to transfer. We give it the R1 vector, the R2 vector, and the vacant focus, and we will be plotting in blue to match our color scheme. And there we go. This is the vacant focus point we selected, and it corresponds to this elliptical transfer, which has a short way in the E1 region and a long way in the E3 region. Similarly, we can pick a point from the E2, E4 branch. We'll take the 850th point, which puts us somewhere up here. We run the plotting code again. Here is the vacant focus location we dialed in, and that results in this red elliptical transfer with the short way in the E4 region and the long way in the E2 region. We can do the exact same thing for the H2 and H1 families. We'll start with H2 and pick a value from the left branch of the vacant focus hyperbola. So the 50th element of this array puts us somewhere down here. We again run the plotting code, and there we go. Here's our vacant focus, and here is the resulting transfer in the H2 region. Finally, we'll pick a value from the H1 branch, let's say the 900th value, that puts us somewhere up there. We plot again, here's our vacant focus, and here is the resulting hyperbolic transfer. As we start moving this vacant focus up towards F, what we expect is that this hyperbolic transfer comes closer and closer to the central body. So as an example, here's the vacant focus corresponding to this transfer, and here's the vacant focus corresponding to this transfer. And as we keep going along, moving progressively towards the filled focus with our vacant focus, this hyperbola comes closer and closer to the perimeter of our transfer triangle. Similarly, if we drop down the H1 vacant focus towards this F0 star, we expect this H1 hyperbolic transfer to flatten out and more closely approximate a straight line transfer from P1 to P2. So here we have two additional vacant foci dropping towards F0 star, and we can see, as predicted, the hyperbolic transfer starts to flatten out and more closely approximate this straight line as we approach the non-physical V infinity solution.